Analysis and design of isolated footings. So this is our lesson for today. Now, isolated footings are also known as spread footings. These are footings that carries one column. So example na mga isolated footings, meron tayong mga square, rectangular, or circular na isolated footing. So nagbabari yung shape niya. Nagbabari rin yung kanya column location. Pwedeng nasa center yung column, or pwedeng eccentric siya towards one edge or even towards a corner. When designing an isolated footings, we have several design considerations. I listed some of them here. First is we need to know what are the loads and load combinations that we should be considering. What is the contact pressure, and we will compare it with the soil bearing capacity. Number 3, we have to know what is the concrete shear capacity, and of course, we need to know how much flexural reinforcement should we provide. And sometimes, load transfer is also a concern, so this is about the design dowels. Contact pressure versus bearing capacity. This will give us the footing size, or the width and the length of the footing if it is rectangular, or simply the width if it is square. Concrete shear capacity will give us, or will guide us in how to get the thickness of footing. Flexural reinforcement, of course, gives us the number of rebars or the spacing of rebars that we will use. Let's review certain things about the load combinations. What are the load combinations that we use when we design or analyze footing? So these are snippets from our structural code. The first one, these are the ultimate load combinations, and we use it when we design the concrete. We will be using this to check the shear in concrete. We also have the basic load combinations and the alternate basic load combinations. These are serviceability combinations, so service loads. We check them, or we use them when we are checking for allowable values like the allowable soil bearing capacity, allowable settlement, and others. As an example for this lesson, let's look at this situation. We have a footing, and it is loaded by a dead load of 300 kilonewtons and a live load of 500 kilonewtons. Other informations about the soil and the concrete unit weight are given. The footing is founded at a depth of 1.6 meters. The allowable soil-bearing capacity is 200 kilopascals. The column that is situated at the center of the footing is 300 by 400 millimeters. So we expect to have a rectangular footing because the column is rectangular. First, let's get the service load. So what is the service load combination? Since we have only dead load and live load, so we just add dead load plus live load, which gives us 300 plus 500. So P will be 800 kilonewtons. And because that is 800 kilonewtons, the contact pressure below that would be P over the area of the footing, or 800 over whatever is the area of the footing. Later, we will see what is the area of the footing. Now, for the ultimate load combination, since we only have dead load and live load, I can see that the governing load combination will be 1.2 times the dead load plus 1.6 times the live load. So 1.2D, so 1.2 times 300 plus 1.6 times 500, which gives us 1,160 kilonewtons. Therefore, P sub U would be 1,160 kilonewtons. And for the ultimate pressure, Q sub U, this would be PU over A, or 1160 over A. And again, we don't know the area of the footing yet, so let's leave it as that. After getting the load combinations that we will be using, the first thing that we need to do is to check the contact pressure versus the soil-bearing capacity. Now, the method that we use here in the Philippines is using the net, or actually this is the effective soil-bearing capacity method. And by that, what I mean is we compare the net contact pressure with the effective soil-bearing capacity. And this effective soil-bearing capacity, we can compute it by subtracting the weight of the soil and the weight of the footing from the allowable soil-bearing capacity. And this one, these are from the column load. There is a problem that we will now be encountering because this is the method that we use here in the Philippines. And that problem is, how do we estimate the weight of the soil and the weight of the footing if the thickness of both the soil and the footing are not given? So the thickness of the footing is not given. The height of the soil is not given. What is only given is the depth of the foundation. So we don't know yet what is the thickness of the footing. So that is now a problem. How would we estimate this weight of soil and footing if the thickness of the footing is not given? So now what we do is we estimate first what is the thickness of the footing. So there are two general methods that is used here in the Philippines. The first method, or actually in other parts of the world, this is also used. We assume that the footing and soil weight is a certain percentage of the loads. For example, I sometimes see the estimation that this weight would be about 10% of P. Another method for this initial calculation is to assume an initial footing thickness. And upon assumption of that initial footing thickness, we need to check later if this assumption holds true. And that is if the required footing thickness is less than or equal to what we have assumed to be the footing thickness. Now, how do we assign or how do we assume this footing thickness? This is actually my preferred way of calculation. So for me, my preferred way is to use a conservative value where what I do is the assumed footing thickness, I set it to the founding depth. This is conservative, and I found that it will always work. Conservative meaning to say we will have a larger size of footing when we do the calculations. But an advantage is that it will always work. Okay? This check will always be realized. Okay, so let's do this. Let's go back to this example. Now, if we do example 1, or the first method, method 1, I know that the load would be 800 kilonewtons. This is the surface load. And if I assume that the weight of soil and footing is 10% of that, so that would give me 80 kilonewtons. Adding all of that, P now would be 880 kilonewtons. Now, this is a gross load because this includes the weight of the footing and soil. What I'll do is I'll compare that with whatever is my allowable load. So I have 880 over the area of the footing must be less than or equal to the original 200. Notice that I did not use the effective soil-bearing capacity here because this is a gross load. Gross means I am including the weight of the soil. So if Q sub K or my contact pressure is based on the gross load, I should be comparing it with a gross value, which is the gross allowable soil-bearing capacity of 200. Computing this, I get the area of the footing must be greater than 4.4 square meters. And this will help me size the footing later. Now, let's repeat the problem, but this time, let's use the second method. The second method is we assume a thickness for the footing. Now, let me assume T is equal to Df. That means that T would be 1.6 meters. Because of that, I can solve for the effective soil-bearing capacity. This would be 200 minus 1.6 times pure concrete, which has unit weight of 24 kilonewton per cubic meter. This will give me 161.6 kilopascals. Okay, now my contact pressure should be less than this value. And for the contact pressure, I will be using net values. So that means 800 divided by the area of the footing should be less than 161.6 kilopascals. This gives me an area of the footing that must be greater than or equal to 4.95 square meters. So as you can see, this condition is quite larger than the previous one of 4.4. But the advantage is this will always work. Next, how do we proportion B and L, or the width and the length? Especially if the column is not a square column. Now, for square columns, we simply get the square root of the footing area, since a square column necessitates a square footing. But what I'm recommending is you proportion the footing such that the cantilevered parts must be equal. So that is my recommendation. This is not actually a requirement for the design, but rather a recommendation that would make our lives easier. Actually, it's based on my experience that the cantilevered lengths must be equal. And what do I mean by this cantilevered lengths? This is the distance from the face of the column to the edge of the footing. These distances, let's label it as x, should be equal. So since they are equal, they must be both equal to x. So let's solve for the relationships. Now, what I could see is this x is equal to L sub y minus C sub y over 2. And this must be equal to this horizontal x, which is L sub x minus Cx divided by 2. Or Ly minus Cy must be equal to Lx minus Cx. This relationship is my recommendation on how to proportion B and N. Let's apply that to our previous problem. So, from our previous example, we know that the area of the footing must be greater than or equal to 4.95 square meters. This comes from method 2 and assuming the thickness is equal to the founding depth. Now, we know that the area is of course B times L. That should be greater than 4.95. From my recommendation, B minus 0.3 is B minus the corresponding column dimension must be equal to L minus 0.4, or L is B plus 0.1 meters. Substituting L to that inequality, we have B times B plus 0.1 must be greater than 4.95. Solving for B, we get B must be a value greater than or equal to 2.175 meters, and L must be a value greater than or equal to 2.275 meters. Now, rounding up to the nearest 10 millimeter increments, we can say B is 2.18 meters and L is 2.28. So now we have a size for the footing. The next step is we check for concrete shear capacity, and this concrete shear capacity will control the thickness of our footing. There are two shear capacities or two shear effects that we will be checking when designing an isolated footing. These are the one-way or the wide beam shear, which looks like this. So let's say we have a footing, and here's the column, and part of the footing can be sheared off. So we will have here a critical section. This is our critical section, and it is located at a distance d from the face of the column. It could be like this, vertical, or it could be in the other direction, like this. The critical section would be here, and still, it would be at a distance d from the face of the column. The distance d is what we refer to as the effective depth. For one-way shear, we use the smaller effective depth. And what do I mean by that smaller effective depth? If I draw the section for isolated footings, we have the bottom bars and the top bars. So this is part of the section of the footing. The effective depth, we will have two values. We have a smaller effective depth, let's call it d sub 2, and a larger effective depth, d sub 1. For one-way or wide beam shear, conservative effective depth could be used, or that would be d sub 2. Another mode of shear failure that we will consider when designing isolated or spread footings is what we call the two-way or punching shear. The two-way or punching shear is when the column punches through the footing pad. So if this is the footing, so let me draw the footing, and this is the column, the critical section for shearing would be around the column like this. This is now the critical section. And its dimensions would be at a distance d over 2 around the column. Or in other words, this length would be c sub x plus d, and the other one would be c sub y plus d. Cx and cy are the column dimensions. That is for a centrally located column. Sometimes the column could be at the edge or at the corner. So for an edge column like this, the critical section would have only 3 sides. So this is now the critical section. And for two-way shear, the effective depth that we use would be the average effective depth. So it means that we get D1 and D2, and then we add them and divide them by 2. So the average effective depth is used for two-way or punching shear. For the one-way or the wide beam shear, it's conservative to use the smaller depth. So let's continue our example. Now, for our example, I drew here the footing with the dimensions that we will adapt. And let's say that the bar diameter is 20 mm and the concrete strength, the material strength is 28 megapascals. Now, let's check first the one-way shear. For one-way shear, we will check two things, but let's check first this critical section. This would be at a distance d from the column face. And what would be the d that we will use? We don't know yet. That would be the smaller d. Okay, our goal here is to get the thickness. Since the thickness is not given yet, we don't know what would be the effective depth. Okay, so, but if we compute this, what would be the width of this area? This would be 0.94 minus d. Now, from our load combinations, we know that P sub u is 1160, and dividing it by the area of the footing, we get the ultimate concrete stress. So we have 1160 over 2.18 by 2.28. So Q sub u, or the ultimate concrete pressure or stress, that would be 233.382 kilopascals. And we need this in order to find what would be the critical shear in our footing. So for one-way shear, let's do a section. Okay, let's get the section here. And if you get the section there, this is for the right side of that part. So here's that critical section. This would be the critical section. So in other words, this would be 0.94 minus 2. That's the length of that part. And we will be exposing here what I like to call the critical shear. And of course, there is contact pressure here that is 233.382 kilopascals. Now, for the design of the thickness of footings, for isolated footings, this critical shear must be less than or at least equal to the nominal capacity of the concrete. Now, for a wide beam shear condition, the nominal capacity of concrete, this would be phi times 1 over 6 square root of F prime C beam width times D. Now, to solve for the critical shear, of course, that would be the sum of this force times, or the resultant of this pressure diagram. So that would be 233.382 times 0.94 minus D times the width of the footing, which is 2.80. And this value must be less than or equal to 0.75. This is the P factor for shear times 1 over 6 square root of the material strength 28 times the width of 2.18. So the width of this section would be 2.18 times D. And to convert into kilonewtons, we need to multiply this value by 1000. Solving for D, we get D should be greater than or equal to 245.17 millimeters. So this is now our design criteria on how to get the effective depth or the thickness later. To get the thickness, so let's reiterate that. This is the setup for the rebars. And for one-way shear, we will use the smaller D. So using the smaller effective depth, we see that the thickness is D plus half of a bar diameter plus bar diameter plus whatever is the concrete cover. So the concrete cover is usually that 75 mm. So thickness must be greater than 245.17 plus a bar diameter of 20 over 2 plus another bar diameter plus concrete cover of 75. So the thickness must be greater than or equal to 350.17 millimeters. So now we have a criteria on how to determine the correct thickness for the footing. A question arises now is, what would be the answer if we went the other way? This is the footing and we considered the critical shear for the other direction. Okay, so how about the other direction? I will leave this as an exercise to you and you will see that you will get the same result. And you need to know why. Can you say, why would it have the same result? It has something to do with the proportioning method that I recommended. Okay, now let's go and check the punching shear. In checking the punching shear, we first need to identify where is the critical section. So this would be the critical section. The dimensions would be 0.4 plus D, and in the other one, this would be 0.3 plus D. 0.4 and 0.3 are the dimensions of the columns in meters. Now, we need to identify two things. The perimeter of the critical section and the area under this critical section. The perimeter would be, let's call it B sub O. This would be twice the sum of 0.4 plus D and 0.3 plus D. So this perimeter, this would be 1.4 plus 4 times the effective depth. The area under this critical section, of course, would be just the product of 0.4 plus D and 0.3 plus D. These are the two things that we need to compute first. Now, in order to check for the punching shear, we have the same thing with the one-way shear, that the critical shear should be less than or equal to whatever is the capacity of the concrete. Capacity of the concrete for punching or two-way shear, this would be P times, instead of 1/6, we have 1/3. Square root of F prime C, D sub O, D. And for our example, the critical shear, this would be P sub U minus Q sub U times A sub O. Why is it like that? P sub U is the original load, the ultimate load. Why do we subtract Q sub U times A sub O? Because that would be, if you draw it, or if you isolate this column and draw the thing in, or draw the, or get the section, this would be the section or the critical section, and you will have the contact pressure here, Q sub U. And we also have here P sub U. And the critical shear, okay, critical shear would be solved by summing of the vertical forces. So by summing up the vertical forces, we get PU minus QU times A sub O is the area under this critical section. Now let me continue our solution. So critical shear, that would be 1160. Remember, that is P sub U minus 233.382, which is our Q sub U, or the ultimate pressure, times A sub O is 0.4 plus D times 0.3 plus D. And this value must be less than 0.5 times 1/3. So this should be 1/3 times square root of the material strength of concrete, which is 28 megapascals, times B sub O times D. And then we don't forget to multiply this by 1000, convert it into kilonewtons. Solving for D, in this equation, and solve for D, first do an equality, and D would be should be a value which is greater than 305.62 millimeters. Now, using D for two-way or punching shear as the average of D1 and D2 from this figure, so this would be D1 would be up to the center of the bottom bars, D2 would be up to the center of the top bars, you will get T should be D plus diameter, bar diameter plus C sub C. So the thickness should be greater than 305.62 plus 20 plus 75, or thickness should be greater than 400.62 millimeter. So in summary, for one-way or wide beam shear, the thickness should be greater than or equal to 350.70 millimeters. For two-way or punching shear, the thickness should be greater than or equal to 400.62 millimeters. As you can see, this condition governs, so the thickness should be greater than 400. So the two-way or punching shear governs the design. So let's use T, or the thickness, to be equal to 410 millimeters. Or the thickness is oftentimes rounded up to the nearest 10 millimeters. Recall previously that we assumed that the thickness should be 1.6 meters or 1,600 millimeters. So we have satisfied the check that the actual T that we will use should be less than or equal to what we have assumed. So this should be okay. So now we can write the footing dimensions, and that is the length is 2.28 meters, the width is 2.18 meters, and the thickness is 410 millimeters. After getting the dimensions, the next step in the design of an isolated footing is solving for the reinforcements. Now, from reinforced concrete design, we have several formulas that we will be using. So when designing a section, and these are the bars, this would be the effective depth, and this would be the width B. The basic condition for the flexural design would be whatever is the critical moment, MU, or critical moment, should be less than or equal to the bending moment capacity of the concrete. Now, as an intermediate step, we solve for R sub n, which is MU divided by PBB squared. And from there, we can get the required steel ratio using this equation or formula. This formula can be found in standard text in reinforced concrete design. And another thing that we need to satisfy is this raw required is limited by a minimum steel ratio, which is the smaller of two values. And those two values are, first, we have the larger of 1.4 over Fi, and the square root of F prime C over 4 times Fy. And the other value would be 4/3 of what is required. And after that, we will use raw, would be the larger of raw min and raw required. Raw is the steel ratio. To get the area of steel required, we multiply raw by B and D, or the number of bars would be AS required divided by the area of a single bar. Now, how do we know where is or what is the critical moment? Critical moment can be found at the face of the column. So if this is the section view, at the face of the column, here lies our critical moment. Okay? Critical is at face of column. Okay? Let's go back to our example, and I have written here the values that we need. First, let's draw the top view of the column and of the footing. And of course, we will be designing two things. There would be a transverse and a longitudinal direction. So the critical moment here, let's call this M1. And for the other direction, again, the face of the column, let's call this M2. Now, given the dimensions, 2.18 and 2.28, I can measure the cantilevered portions. So let's say that the cantilevered portion for M1 is L sub 1 and the cantilevered portion for M2 is L sub 2. So let's solve for the critical moments. For M1, cantilevered portion would be 2.28 minus the dimension of the column 0.4 divided by 2, which gives us 0.94 meters. So M1, this figure, M1 would actually be here. So we just get the moment of the pressure diagram with respect to this section. So M1, that would be 233.382 times the cantilever part, 0.94, times a moment arm of 0.94 over 2, multiplied by the width, 2.8. So the critical moment for the first part, that would be 224.776 kilonewton meter. For M2, cantilevered portion L2 is 2.18 minus 0.3 divided by 2. And of course, this would be 0.94 meters also. Because remember, when we proportion the footing, cantilevered portion should be equal. So M sub 2 now would be 233.382 times 0.94 times a moment arm of 0.94 over 2 times the length on that side is 2.20. So M sub 2 is 235.087 kilonewton meter. Okay, now let us design the section along M1. So this is the section along M1. Let's draw that first. Here's the section. Of course, the thickness is 410 millimeters. And the width of that section would be 2.18 millimeters. Now, for the material properties, F sub C is 28 megapascals. Let's use Fy equals 280 megapascals. This would be given when designing a footing. And the part diameter used is 20 millimeters. And we know from our previous calculation that M1 is 224.776 kilonewton meter. Now for the effective depth, let's use the smaller depth. So we have 410 minus the concrete cover minus 20, the bar diameter minus half of the bar diameter, which is 305 millimeters. So this is the smaller effective depth. Now we can solve for R sub n. So that's mu, or 224.776 times 10 raised to 6 Newton millimeter divided by phi, which is 0.9 for flexure. So we have 2180 millimeters, and d is 305 millimeters, and don't forget to square it. This will give us 1.232 megapascals. Continuing with the reinforced concrete design formulas, the required steel ratio can be computed. So we have 0.85 times the compressive strength of concrete divided by the yield strength of steel times quantity 1 minus the square root of 1 minus twice of 1.232 megapascals divided by 0.85 times 28 megapascals, which is this compressive strength of concrete. From here, we know that the required steel ratio is 0.00452. Now, we need to compare it with the minimum required, which is the smaller of two values, which is the larger of 1.4 over Fy and square root of Fc over 4 times Fy, and 4/3 of what was required. Solving for this, we have 0.005 for this one and 0.00472. Here we have 0.00603. So the larger of these two values is obviously 0.005. And the smaller of 0.005 and 0.00603 is 0.005. So we know that the minimum required steel ratio is 0.005, and we will use rho equals 0.005 because this is the larger between these two. The required steel area is now therefore equal to 0.005 times the width, which is 2180 millimeters times the effective depth of 305 millimeters, which gives us 3,324.5 square millimeters. Continuing, let me rewrite here first what is the required steel area. So the number of bars that we need would be 3324.5 divided by pi over 4 times 20, which is the area of the bar. This would be 10.58, or we say N is 11 pieces of 20 mm bars. Now, to get the spacing of these bars, so let's imagine this is a section and these are the bars. We have here a concrete cover, and up to the center of that bar, we have the bar diameter over 2. And of course, that would be on both sides. And here we have n-1 spaces. So to compute the center-to-center spacing of the bars, spacing would be B minus twice the concrete cover minus 1 bar diameter divided by the number of spaces. So S would be 2180 minus twice of concrete cover. So for footings, usually concrete cover is 3 inches or 75 millimeters because it's directly poured or exposed to soil. So minus 20 mm, and we have 11 minus 1. Calculating this spacing, we should be getting a value of spacing is 201 millimeters. Okay, so I will leave the other direction for you. Okay, that would be the number of pieces for M2, and should be about 12 pieces. That's the section in the other dimension here. So as practice, try to solve for the number of bars required in that other section. So in summary, this is my footing dimensions. We have 2.80 meters and 2.28 meters. The thickness of the footing required is 410 millimeters. And let's say this dimension would be 280 millimeters. The bottom bars, these are 11 pieces of 20 millimeter bars. And the top bars are 12 pieces of 20 millimeter bars. And of course, as per the original problem, it is founded at a depth of 1.6 meters. So that ends our or my lesson for this is actually an introduction to the design of isolated footings. So we checked several things. We identified the load combinations. We did the sizing using the soil bearing capacity. We did a sizing for the thickness using the shear capacity, and we did the rebars and spacing. What's not included in this lesson, this is just an introduction, is how do we design the dowels. So I hope you will stay for more lessons about footing designs under the principle of foundation engineering course.
Like mo yung video kung ayos. Pag hindi, pag mo i-dislike, leave ka ng comment kung bakit, ha? Sige na, subscribe.